Have you ever wondered what makes an equation so important that it's carved into the stone floor of Westminster Abbey, alongside the tomb of Isaac Newton? There, in the heart of British history, lies the Dirac Equation, silent, simple, and yet profoundly powerful, because this single equation didn't just solve a problem, it changed the very structure of physics and revealed, for the first time, the existence of an entirely new form of matter: antimatter. In 1928, at just 25 years old, Paul Dirac unified the strange new world of quantum mechanics with Einstein's special relativity, publishing his now famous equation in a groundbreaking paper titled The Quantum Theory of the Electron. Born in 1902 in Bristol to a very strict father, Dirac often chose silence over speech, retreating into introspection and deep thought. These qualities would later shape his unique and unshakable approach to physics. He believed, above all, that the laws of nature should be guided by elegance, once writing, "It's more important to have beauty in one's equations than to have them fit experiment." His greatest breakthrough didn't come from data or measurement, but from that belief, the conviction that mathematics itself could uncover nature's deepest truths. In this two-part series, we'll follow the journey that led to Dirac's extraordinary achievement. In this first video, we'll explore the deep tensions between quantum mechanics and relativity, the failures of earlier attempts to bridge them, and the brilliant insight that set Dirac apart. In part 2, we'll then solve the Dirac equation itself and uncover two astonishing consequences: the prediction of antimatter and the natural emergence of quantum mechanical spin. Our story picks up in 1927, at one of the most important gatherings in scientific history, the Solvay Conference. There, the greatest physicists of the day, including Einstein, Schrödinger, Heisenberg and Bohr, came together to debate the strange new laws of quantum mechanics. It was at this conference that Paul Dirac, still a young and relatively unknown figure, was asked by Niels Bohr what he was working on. Dirac replied, "I'm trying to get a relativistic theory of the electron." Bohr famously responded, "But Klein has already solved that problem." He was referring to the Klein-Gordon equation, one of the earliest attempts to build a relativistic quantum theory. But Dirac disagreed. He was convinced that Klein and Gordon's approach was flawed, and that it was fundamentally inconsistent with the new quantum mechanics that was taking shape. To understand why Dirac was dissatisfied, and to truly appreciate the revolutionary step he would soon take, we need to first review the foundations of quantum theory as they stood in 1927, and that means beginning with the Schrödinger equation. The Schrödinger equation lies at the heart of quantum mechanics. It's a wave equation that is first order in time derivatives and second order in space derivatives, linking the evolution of a particle's quantum state to its energy and momentum. The general approach is to define the potential energy of the system, substitute this into the Schrödinger equation, and then solve for the wave function psi of xt. The wave function contains all the information about the system, but it's not directly measurable. Instead, by taking the modulus squared of the wave function, we obtain the probability density, a real, positive quantity that tells us where we're most likely to find the particle in space. Now, it's informative to see how the Schrödinger equation naturally arises. We start from the familiar non-relativistic energy-momentum relation E equals p squared divided by 2m plus v, where p is the momentum of the particle, m is the mass, and v is the potential energy. In quantum mechanics, we then promote the energy and momentum to operators that act on the wave function. Specifically, the energy E becomes I h bar d by dt, and the momentum becomes minus I h bar del, where del is the gradient operator. Substituting these into the classical energy equation and allowing them to act on the wave function leads directly to the famous time-dependent Schrödinger equation, where the del squared operator acting on the wave function is defined in terms of second-order spatial derivatives. A key point to re-emphasise at this stage is that the Schrödinger equation is first order in time derivatives. It only involves the first derivative of the wave function with respect to time. This feature is crucial because it means that the evolution of the wave function is fully determined by its value at a single instant, for example at t equals 0. Once you specify the wave function at one moment, the Schrödinger equation predicts everything that happens later without needing any additional information, such as the initial time derivative. We can see this even more clearly by viewing the Schrödinger equation as a first-order ordinary differential equation in time. If we define the operator inside the brackets as the Hamiltonian operator and rearrange slightly, we find the following expression. And this is analogous in form to the equation d by dt of y of t equals a y of t, where a is some operator or constant. The general solution to such an equation is y of t equals e to the at y of naught, and this shows explicitly that knowing y of naught, the value of the function at t equals 0, completely determines its future evolution. By direct analogy, if the Hamiltonian is time independent, then the solution to the Schrödinger equation can be written in the following form. Here, the operator exponential depends only on the Hamiltonian and the time. There's no additional hidden integration constant that would require knowledge of the derivative of the wave function at t equals 0. So this is telling us that once you specify the initial wave function and normalise it so that the integral of the modulus squared over all space equals 1, then the Schrödinger equation tells you everything about how the quantum state will evolve. Now, because the wave function contains the complete description of the system, it's natural to ask, what physical meaning can we extract from it? As we've already seen, taking the modulus squared of the wave function gives the probability density, which we call ρ of xt. Importantly, this expression is always positive or 0, and the reason is simple. The modulus squared of the wave function is defined as the complex conjugate of the wave function multiplied by the wave function itself. And when you multiply a complex number by its own complex conjugate, the result is the sum of the squares of its real and imaginary parts, both of which are real and non-negative. Thus we can say that the probability density is greater than or equal to 0 for all x and t, as is required for a sensible probability interpretation. However, probability isn't just about where the particle is likely to be. It also has to be conserved. It can't just vanish or pop into existence out of nowhere. You can think of the probability density as describing how dense the cloud of probability is at each point in space. And if the cloud gets thinner or thicker in one place, it must be because probability is flowing in or out of that region. To capture that idea more precisely, we introduce the probability current, a vector quantity that tells us how the probability moves around space. Now, imagine choosing a fixed region of space, it could be a sphere, a cube, any shape you like, and let's label it V. The total probability of finding the particle somewhere inside V at time t is the integral of the probability density ρ over that region V. Now, because probability can't vanish into thin air or appear out of nowhere, any change in the probability inside V must be due to probability flowing across the boundary surface S of V. At each point on the surface, the dot product j.ds tells us how much probability is flowing through a tiny patch ds per second, and in which direction. And it then follows that the rate at which the total probability inside V changes is equal to minus the total probability flowing out across the boundary. In mathematical terms, we can write this in the following form, where the left-hand side represents how the total probability inside V changes over time, while the right-hand side represents the net outward flow of probability across the surface S. The minus sign simply reflects the fact that if probability flows outward across the boundary, then the total probability inside V decreases. We can illustrate this process with 4 subplots. The top left plot shows a 3D probability cloud moving towards a spherical region V, while the top right shows a 2D cross-section with the probability density represented by a heat map crossing a circular boundary, with arrows indicating the local current flow. The bottom left plot shows how the total probability inside V changes over time, and the bottom right compares the rate of change inside V with the total outward flow across the boundary. The two curves are exactly equal and opposite, showing that probability is conserved. Any loss inside the region exactly matches the amount flowing out. So let's now return to our probability conservation equation. We can then use one of the great theorems of vector calculus, the divergence theorem, to turn the surface integral appearing on the right hand side into a volume integral. In other words, we can say that the surface integral over S of j dot ds equals the volume integral over V of del dot j. Here, del dot j, the divergence of j, tells us how much probability is flowing outward or inward at each point inside the region. And if we then use this relation in our conservation equation, we find the following blue expression, and we see that we have now written our probability conservation law entirely as an integral over the same region of space V. Now, because the region V is fixed, its shape and location don't change with time, we can move the time derivative inside the integral, in which case we find the following expression. Now, if an integral of one function equals the integral of another over every possible region V, then those two functions must be equal at each point. Therefore, we conclude that the partial derivative of the probability density ρ with respect to time, plus the divergence of the probability current J, is equal to 0, and this equation is known as the continuity equation. This equation lies at the heart of probability conservation. At each point x, any increase in probability density must be exactly balanced by a net inflow of current, and any decrease by a net outflow. Okay, so armed with the continuity equation, let's now derive an expression for the probability density and current by using the free particle time-dependent Schrödinger equation with the potential energy set to 0, which takes the following form. If we then take the complex conjugate of this equation, which involves switching i's for minus i's, then we find the following green expression. Next, if we multiply both sides of the first expression by the complex conjugate of the wave function, and multiply both sides of the second by the wave function, and then subtract and rearrange, we arrive at the following expression. We then note that we can write the left-hand side as I h bar d by dt of the product of the complex conjugate of the wave function with the wave function itself, whereas the right-hand side can be written in the following form. If we then rearrange this so that the right-hand side is equal to 0, and then compare with the continuity equation we derived earlier, we immediately see that the probability current is given by the following blue equation, whereas the probability density is the familiar expression equal to the modulus squared of the wave function. Thus, we see that according to the Schrödinger equation, once we've determined the wave function, we can compute both the probability density and the probability current. We again emphasise that the form of the probability density resulting from the Schrödinger equation implies that it is always greater than or equal to 0. To make this even more concrete, let's look at a simple example, a plane wave solution of the following form, where p is the momentum of the particle, E is the energy, and n is a normalization constant. Substituting this into the expression for the probability density, we find the following result, which is a constant everywhere in space. And the corresponding probability current works out to be equal to the probability density multiplied by p over m. And this shows that a free particle with momentum p moves steadily through space at velocity p over m, carrying a constant cloud of probability along with it. This beautiful intuitive picture of probability flowing smoothly and remaining positive lies at the very heart of quantum mechanics, but it also rests delicately on the specific structure of the Schrödinger equation. However, there's a catch. Despite its remarkable success, the Schrödinger equation is inherently non-relativistic. It assumes that the energies and velocities involved are much less than the speed of light. This limitation becomes evident when we remember that the Schrödinger equation is based on a classical Hamiltonian with the kinetic energy term equal to p squared over 2m, where p is the momentum and m is the mass. And this simply isn't consistent with Einstein's special relativity. For a truly relativistic theory, we must start with the correct energy-momentum relation, E squared equals P squared C squared plus M squared C to the 4. And physicists quickly realised that if quantum mechanics was going to describe fast-moving particles like electrons, then it would need a new kind of relativistic wave equation. Schrödinger himself first attempted to build one, but when his approach failed to reproduce the correct fine structure of the hydrogen atom, he abandoned it and focused instead on his famous non-relativistic equation. The idea, however, was then independently developed by Oscar Klein and Walter Gordon. Starting from the relativistic energy-momentum relation, they promoted E and P to quantum operators acting on the wave function, just as we did earlier with the Schrödinger equation. Then, following the same steps by defining the energy and momentum operators, they arrived at the following equation, which is known as the Klein-Gordon equation. And you'll often see this written in an equivalent rearranged form as follows. Now, while the Klein-Gordon equation is indeed relativistically invariant by construction, it introduced several significant problems. Firstly, the equation is second order in time derivatives, since it contains d2 psi by dt squared. As a result, in order to determine the future state of the system, it's necessary to specify both the initial wave function at t equals 0, as well as the time derivative of the wave function at t equals 0. In other words, unlike the Schrödinger equation, the wave function alone is not sufficient to fully determine the quantum state of the system. This situation is similar to classical mechanics, where Newton's second law states that the force acting on a mass m is equal to the mass times its acceleration, where acceleration is defined as the second derivative of position with respect to time. To predict the motion of a particle, it's necessary to specify both the initial position and the initial velocity. In contrast, as we've already seen, the non-relativistic Schrödinger equation is first order in time derivatives, meaning that specifying the wave function at t equals 0 is enough to completely determine the future evolution of the system. However, in the case of the Klein-Gordon equation, because it's second order in time derivatives, the wave function alone is not sufficient. To fully specify the quantum state, one must also provide the initial time derivative of the wave function, and this extra information cannot be extracted from the initial wave function alone. Thus, the Klein-Gordon wave function fails to provide a complete description of the system's quantum state, which is inconsistent with one of the central principles of quantum mechanics, that the wave function by itself should fully describe the physical system. But this isn't the only issue. Another significant issue arises when we consider solutions to the Klein-Gordon equation. For example, the Klein-Gordon equation has plane wave solutions of the following form, and if we sub this into the Klein-Gordon equation and rearrange slightly, we find the following expression. And so we see that this implies that the plane wave solutions to the Klein-Gordon equation satisfy the Einstein energy-momentum relation. Taking the square root, we find that the energy associated with the wave function is given by plus or minus the square root of p squared c squared plus m squared c to the 4. This immediately reveals a serious problem. For every positive energy solution, E greater than 0, there is a corresponding negative energy solution, E less than 0. If negative energy states were allowed in a single particle interpretation, a particle could decay into lower and lower negative energy states indefinitely, emitting unlimited amounts of energy, something completely at odds with physical observation. However, the difficulties did not stop there. Further complications arise when it comes to the interpretation of probability. For the Schrödinger equation, the continuity equation naturally leads to a positive definite probability density, ensuring that probability is always positive and meaningful. However, this is no longer the case with the Klein-Gordon equation. To see this, We start with the Klein-Gordon equation. If we then take the complex conjugate of this equation, we find the following blue expression. Next, if we multiply the first expression by the complex conjugate of the wave function, and multiply the second by the wave function, and then subtract the second from the first, we find the following yellow expression. Next, we recognise that the first term can be rewritten as a single total time derivative using the product rule. Similarly, the spatial terms can be grouped together into a total divergence term, and if we then rearrange, we find the following blue expression. And then we can compare this with the continuity equation that we derived earlier. By comparing the two expressions, we see that we can identify the form of the probability density and probability current. Now, if we did this carefully to ensure that ρ and j have the correct units, we would find the following exact expressions. Now, here is the crucial and damning point. Unlike the Schrödinger probability density, which is positive definite, the Klein-Gordon probability density can in fact be negative. One way of seeing this is to consider a plane wave solution of the following form. If we sub this wave function into the Klein-Gordon probability density and simplify, we find the following result. And so we see that the probability density is proportional to the energy of the particle. And as we've already seen, the energy is given by the following expression, which includes negative energy solutions. And this then implies that the negative energy solutions have negative probability densities. This fundamentally undermines the interpretation of the wave function as a probability amplitude, making it difficult to maintain consistency with the principles of quantum mechanics. Probabilities within the context of quantum mechanics are supposed to represent real, measurable chances of finding a particle in a given region of space. As a result, the Klein-Gordon equation, despite its elegance, fails to support a consistent single particle quantum theory. And to make matters even worse, the Klein-Gordon equation also fails to predict the correct energy levels for the hydrogen atom, and it also overlooks key features such as spin and fine structure, further limiting its viability as a fundamental description of relativistic particles. And it was Paul Dirac who fully recognised these shortcomings. We can now understand more clearly Dirac's response to Bohr at the 1927 Solvay conference. If you recall, when Bohr asked Dirac what he was working on, Dirac replied, "I'm trying to get a relativistic theory of the electron," to which Bohr answered, "Klein has already solved that problem." But we can now see why Dirac disagreed. He had convinced himself, much as we have just argued, that the approach of Klein and Gordon was fundamentally flawed and inconsistent with the principles of the newly developed quantum mechanics. Dirac realised that a new approach was required. In particular, Dirac sought a wave equation that would be first order in time derivatives, just like the Schrödinger equation, so that the wave function alone would fully determine the system's future evolution, while also preserving a positive definite probability density and allowing the wave function to retain its interpretation as a true probability amplitude. But he aimed even higher. The equation needed to be fully consistent with special relativity, meaning that space and time had to be treated on equal footing. And so the equation had to be linear in both space and time derivatives. Dirac, often seen as quiet and introspective, had already watched several of his European contemporaries make landmark contributions. Now, he set his sights on an ambitious goal, one that would lead to one of the most profound equations in all of physics. So, what did Dirac do? Well, before uncovering the magic, just a quick reminder, if you're enjoying this exploration and want more deep dives into the ideas that shaped modern physics, then please consider hitting the like button and subscribing. It really helps the channel grow and reach more people. But now, let's get back to the story. Well, first of all, if the equation is to conform with the principle of relativity, then it must contain a Lorentz invariant expression of energy and momentum. In other words, it must apply to the relativistic energy-momentum relation, E squared equals P squared C squared plus M squared C to the 4. Now, a natural start point might have been to write the energy as the square root of P squared C squared plus M squared C to the 4, and then promote the energy and momentum into operators acting on the wave function psi, where the momentum squared operator can be expressed in terms of its x, y, and z components. Then, if we make the standard substitution for the energy operator, we arrive at the following blue expression. However, this is not satisfactory for a few reasons. Firstly, from a mathematical perspective, it is not clear how to deal with the square root of an operator. Also, from a relativistic perspective, energy and momentum do not appear in a symmetric way. Dirac realised that if the square root could somehow be rewritten in a linear form involving px, py, and pz, then this might solve the problem. For Dirac, this was the crucial point. But how could he do it? Dirac's great insight was to write the energy, E equals the square root of P squared C squared plus M squared C to the 4, as a linear combination of Px, Py, Pz, and Mc squared, proposing the following form, where alpha x, alpha y, alpha z, and beta were unknown constants that would need to be determined. Then, to ensure that this is consistent with the Einstein energy-momentum relation, and to determine the alpha and beta coefficients, Dirac squared both sides of the equation. Expanding the right leads to the following beautiful expression, and this must be equal to px squared plus py squared plus pz squared, all multiplied by c squared, plus m squared c to the 4. Now, in order for the left and right hand sides to match, certain constraints are placed on the alpha and beta coefficients. Firstly, we see that alpha x squared, alpha y squared, alpha z squared, and beta squared must be equal to 1. In addition, in order for certain cross terms to vanish, we require certain combinations, such as alpha x times alpha y plus alpha y times alpha x, to vanish, and similarly for combinations involving alphas and betas. Next, Dirac realised that if the alphas are ordinary numbers, then the only way of satisfying a relation like alpha x times alpha y plus alpha y times alpha x equals 0 is if either alpha x equals 0 or if alpha y equals 0. But this poses a problem, as we've already seen that one of the constraints is that alpha x squared equals alpha y squared equals 1, and so it would appear that ordinary numbers cannot satisfy this relation. However, Dirac asked himself an important question. What if alpha x, alpha y, and alpha z were not numbers, but rather matrices? Then it can indeed be true that alpha x times alpha y equals minus alpha y times alpha x, while still satisfying the relationship alpha x squared equals alpha y squared equals 1. So let's consider this possibility. The first thing that we can do is rewrite the constraint conditions in the following compact form, where the indices I, j equals 1, 2, 3 correspond to x, y, and z respectively, and where we have defined alpha 1 equals alpha x, alpha 2 equals alpha y, and alpha 3 equals alpha z. We also introduce the notation I to represent the identity matrix, a matrix filled with zeros except for ones along the diagonal. The natural question is then to ask, what set of matrices satisfies these relations? A well-known example with similar algebraic properties is the set of 2x2 Pauli matrices sigma x, sigma y, and sigma z, which had already been introduced in the context of spin in non-relativistic quantum mechanics. These matrices are quite unusual. Each one squares to the identity matrix, and when you multiply two different Pauli matrices, swapping the order flips the sign. Regardless of whether Dirac had previously encountered them, he later claimed to have discovered them independently, it seems likely that he would have considered whether 2x2 matrices could satisfy the required constraints on alpha and beta. For example, if we multiply sigma x and sigma y, we get the following expression, and carrying out the matrix multiplication results in the following expression. On the other hand, if we consider the reverse order, sigma y times sigma x, then we find the following expression, and this is simply equal to minus sigma x times sigma y. And so we see that sigma x and sigma y anti-commute. In other words, sigma x times sigma y equals minus sigma y times sigma x. And it's easy to show that the same property is true of the other combinations of Pauli matrices. In addition, if we take, for example, sigma x squared and perform the matrix multiplication, then we end up with the following matrix, which is the identity matrix, which we can write as I subscript 2, with the 2 reminding us that it's a 2 by 2 identity matrix. The identity matrix has the special property that when you multiply a column vector by it, you get the exact same column vector back. You can think of the identity matrix as the matrix equivalent of the number 1. Similarly, it can be shown that sigma y squared and sigma z squared are also equal to the identity matrix. And so if we return to our initial set of alpha and beta constraints, then we see that the fact that the Pauli matrices square to the identity matrix looks identical to the constraint that alpha squared equals I. And if we look at the anti-commutation properties of the Pauli matrices and rearrange them slightly, then this also perfectly matches one of the alpha constraints. And so it looks like sigma x, sigma y and sigma z might perfectly satisfy the conditions required of alpha x, alpha y and alpha z. But what about beta? We see from our set of constraints that we require 4 matrices, not 3. More specifically, we need a 4th matrix beta that also anti-commutes with alpha x, alpha y and alpha z. And if alpha x, alpha y and alpha z are indeed sigma x, sigma y and sigma z, then we can rewrite our alpha beta constraint explicitly in terms of the Pauli matrices. So let's now see if we can find such a matrix. To do this, we will assume that the beta matrix has the following general form, where A, B, C and D are constants that we will attempt to fix by applying the anti-commutation constraints. For example, if we sub in our expression for beta into the sigma x anti-commutation relation, we find the following expression. And then if we perform the matrix multiplication and then add together the 2 matrices, then according to the anti-commutation constraint, this should be equal to the empty matrix 0, 0, 0, 0. This then places a set of constraints on A, B, C and D. And if we then impose these constraints on our beta matrix, we find the following result. So now we just need to find A and B. To do this, we can consider the anti-commutation relation between beta and sigma y. And if we then sub in the matrix forms and perform the matrix multiplication and add together the resulting matrices, we find the following result. And this must be equal to the 0 matrix. And so we see that in this case, the constraint is that B must be equal to 0. And so our beta matrix simplifies further, and we end up with the matrix A, 0, 0, minus A. Finally, we consider the anti-commutation relation with sigma z, and if we sub in the matrix forms, perform the multiplication, and add, then we see that the constraint is that A equals 0, and thus the beta matrix is forced to be the 0 matrix with all entries equal to 0. But if you recall, we also require that beta squared gives the identity matrix. And so we conclude that it's not possible to find a 4th 2 by 2 matrix that satisfies the required anti-commutation relations alongside the Pauli matrices. Naturally, one might next wonder whether 3 by 3 matrices could provide a solution. However, 3 by 3 matrices are still too small to accommodate the structure needed. But what about 4 by 4 matrices? It turns out moving to 4 dimensions provides exactly the extra freedom needed to solve the problem. More specifically, one set of 4 by 4 matrices that works can be constructed by embedding the Pauli matrices in the following way. Alpha x is built by embedding sigma x, alpha y by embedding sigma y, and alpha z by embedding sigma z, as shown here. Finally, the beta matrix is constructed by embedding the 2x2 identity matrix along with the negative of the identity matrix. We can verify that these matrices work by explicitly calculating, for example, alpha x times alpha y plus alpha y times alpha x, in which case we find the following matrix expression. And if we then perform the matrix multiplication and then add together the resulting matrices, we find the following expression. And then by using the Pauli anti-commutation relations, we see that this becomes the zero matrix as required. It's important to note that although the calculations above involved matrices that looked like 2x2 structures, they are actually 4x4 matrices, since each entry in the 2x2 layout is itself a full 2x2 matrix. This construction is known as block matrix form. Similar calculations can be done for other pairs of alpha matrices, and in each case we find that the Dirac 4x4 matrices satisfy the required anti-commutation relations. Next, we can also check alpha x squared, and if we sub in the matrix form and perform the multiplication, we see that we end up with the 4x4 identity matrix. And the same is true for alpha y squared and alpha z squared. We can also check beta squared, and we see that we end up with the 4x4 identity matrix as required. Finally, we can check the anti-commutation of alpha and beta. For example, we see that alpha x beta plus beta alpha x is equal to the zero matrix as required. And similar calculations hold for alpha y and alpha z with beta. And so we see that this particular set of 4x4 matrices perfectly satisfies all the constraints that arose from the linearized form of the energy-momentum relation that Dirac postulated for his equation. Now, it's important to note that while this particular representation satisfies the necessary conditions, many different sets of matrices, related by similarity transformations, can also satisfy these constraints. Right. So we're now ready to return to Dirac's original goal, to find a relativistic wave equation that is linear in both space and time derivatives. If you recall, Dirac proposed that the energy can be written in the following form, and we've just discovered that the alpha and betas are 4x4 matrices. The next step is to write this as an operator equation by promoting the energy and momentum to operators. If we then make the standard substitutions, we find the following green expression. Now we can write this in a more compact form by defining a vector containing alpha x, alpha y and alpha z, and also introduce the gradient vector. It then follows that the dot product between these two vectors takes the following form. Comparing this with our earlier green expression, we see that we can now rewrite it compactly in the following form. And this is the equation we were searching for. This is the Dirac equation, a fully relativistic equation that is first order in both space and time derivatives, and that includes the introduction of a novel 4x4 matrix structure. Now, if you've come across the Dirac equation before, you might not recognise the equation in the form written here. So, can we re-express this in a more familiar, compact form? Well, the answer is yes. So let's take a moment to show how we can rewrite the equation even more compactly. If we take the Dirac equation written in component form and then multiply from the left by beta, we find the following blue expression. Next, we can define a set of four matrices, known as gamma matrices, which are constructed from the alpha and beta matrices. Then we can use the fact that beta squared equals the identity matrix, and then we can rewrite our equation in the following form. The next step is to introduce a new object called a 4 vector, which we will denote by gamma superscript mu, which contains gamma naught, gamma 1, gamma 2 and gamma 3. And similarly, we also define a 4 vector of partial derivatives, which we can write compactly in the following form. This then allows us to rewrite the Dirac equation in a compact and elegant form involving a summation over mu. Now, it's standard convention not to write the summation symbol explicitly, but instead to leave the summation implicit whenever an upstairs and downstairs index are contracted together, as is the case with the mu in this expression. This is known as Einstein's summation convention, and therefore we can write the Dirac equation even more concisely in the following form. Next, if we divide through by c, we find an even more common expression of the Dirac equation, and this is known as the covariant form of the Dirac equation because it is manifestly Lorentz invariant, and its structure remains unchanged under transformations between different reference frames. The index mu labels components of a 4-vector, and repeated indices are summed over, as already mentioned, according to the Einstein summation convention. Now, it's important to note that the gamma mu are not ordinary vectors, but matrices, the gamma matrices, which ensure that the equation respects Lorentz invariance, the principle that the laws of physics are the same for all inertial observers. To simplify things further, physicists often work in natural units, where h bar equals c equals 1. This tidies up the equation even further, and in these units, the Dirac equation takes the following elegant form. Finally, if we rearrange the Dirac equation and then introduce the following shorthand notation, then we are able to write the Dirac equation in its most compact form. And it's in this form that we find the Dirac equation etched into the stone floor of Westminster Abbey, a lasting tribute to one of the most profound equations in the history of physics. Okay, but what exactly is this equation telling us? And how can we be sure that it truly provides the correct relativistic description of the electron? Well, as we've already seen, the alpha and beta matrices appearing in the Dirac equation must be 4x4 matrices, and therefore it follows that the wave function itself must have 4 components. We see that the requirements of relativity, combined with the demand that the equation be first order in both time and space derivatives, have naturally led us to a 4-component wave function. This object is known as a Dirac spinor, and we'll have much more to say about what a spinor is and how to interpret it in the next video. For now, it's important to know that the components are complex valued functions. Now, one of the major issues we encountered earlier with the Klein-Gordon equation was that the probability density could become negative, undermining its interpretation as a true probability. One of Dirac's key motivations was to fix this problem, and now that we have the Dirac equation and the structure of the wave function in hand, we can ask the following question. What is the probability density corresponding to the spinor wave function in the Dirac equation, and is it positive definite? To answer these questions, we need to derive an expression for the probability density in terms of the spinor wave function. The procedure is similar in spirit to what we followed for the Schrödinger and Klein-Gordon equations. However, there is an important new feature. The wave function is now a 4-component spinor, and if you recall, when dealing with the Schrödinger equation, the probability density was simply given by the modulus squared of the wave function, which involved multiplying the wave function by its complex conjugate. However, this product does not make sense for Dirac spinors, as this would mean attempting to multiply 2 incompatible objects together. And so it follows that when dealing with spinors, we need to define an analogue of complex conjugation that takes into account the 4-component form. Rather than the complex conjugate, we define the Hermitian conjugate, which is written in the following form. This involves taking the complex conjugate and then transposing the spinor. If we then apply this operation to our spinor, we get the following result, and we can then use this to define the Hermitian conjugate of the Dirac equation. So if we start with the Dirac equation in component form, and then take the Hermitian conjugate of the entire equation, this involves switching the i's for minus i's, daggering the spinors and matrices, and switching the order of spinors and matrices, and we end up with the following relation. Next, we can explicitly check that each of the alpha and beta matrices are Hermitian, by which we mean that if you take the Hermitian conjugate of the matrix, you get back the exact same form that you started with. To see this explicitly, let's look at the example of alpha y. If we then write out the full 4x4 version of alpha y, and then take the Hermitian conjugate of this matrix, then this involves taking the complex conjugate and the transpose at the same time, in which case we end up with the following expression, and we see that this is just what we started with, alpha y. And so we see that alpha dagger y is equal to alpha y, and the same is true for the other alpha and beta matrices. So what does this mean? Well, it means that if we take the Hermitian conjugate expression of the Dirac equation, we can then write this in the following equivalent form. Next, consider forming the difference between psi dagger multiplied on the left of the original Dirac equation minus psi multiplied from the right on the Hermitian conjugate of the Dirac equation. We can then write this in the following form. And then we note that the left-hand side can be written as a total derivative with respect to time of the product of psi dagger times psi. As for the right-hand side, a little algebra and rearrangement reveals the following beautiful expression. We further observe that this can be compactly written as a dot product between the gradient vector and the alpha vector of matrices. And thus we arrive at the following compact purple expression. And if we then rearrange this so that the right hand side is equal to 0, and then divide through by I h bar, we arrive at the following green expression. Next, if we compare this with the continuity equation that we derived earlier, then we immediately can read off expressions for the probability density and the probability current. But is the probability density always non-negative? To answer this question, we can express the probability density in terms of the components of the Dirac spinor. If you recall, the Hermitian conjugate of the spinor is given by the following expression, and therefore when we form the probability density, we obtain the following blue expression. And we see that this is simply the sum of the modulus squares of each of the component complex valued functions of the Dirac spinor. And since the modulus squared of a complex number is always non-negative, it follows that the probability density is always greater than or equal to 0. And so we see that Dirac succeeded where Klein and Gordon had struggled. He created a fully relativistic wave equation that was first order in time, preserved a positive definite probability density, and naturally required a new kind of wave function, a 4-component spinor rather than a single complex number. Alongside this, Dirac introduced a set of matrix-valued operators, the gamma matrices, which act on the spinors to ensure the theory remains consistent with the principles of special relativity. This achievement was remarkable, not only because it solved the immediate problems of quantum mechanics and relativity, but because it unveiled a deeper, hidden structure within the mathematics of nature itself. Dirac's equation combined the ideas of quantum mechanics and special relativity into a single, elegant framework, and in doing so, laid the foundation for much of modern physics. But this naturally raises new and profound questions. What does this 4-component object actually describe? What do its components mean physically? And what can we learn by solving the Dirac equation? In the next video, we'll tackle those questions head on. We'll solve the Dirac equation, uncover the meaning of the spinor components, and reveal something truly extraordinary, that Dirac's equation, purely from the logic of mathematics and symmetry, predicted the existence of an entirely new form of matter, antimatter. And speaking of uncovering hidden structures, if you've enjoyed seeing how calculus and matrices quietly underpin the deepest laws of nature, then you'll love exploring them more with today's sponsor, Brilliant. Brilliant helps you get smarter every day with thousands of interactive lessons in maths and science. Their app makes it easy to learn anywhere right from your phone with fun, hands-on lessons you can dip into whenever you have time. Each lesson is packed with interactive problem solving that lets you play with concepts, a method proven to be 6 times more effective than just watching lecture videos alone. If you want a deeper grasp of the kind of maths we touched on today, I highly recommend Brilliant's calculus course. It will help you lay a strong mathematical foundation by mastering the basics of differentiation and integration, build deeper intuition for physical principles, and unlock more advanced topics in physics, all helping you on your journey to understand the laws of the universe. And right now you can try everything Brilliant has to offer completely free for 30 days. Just head to brilliant.org/physics explained, scan the QR code on the screen, or click the link in the description. You'll also get 20% off an annual premium subscription if you decide to stick around. So thanks for watching, and until next time, goodbye.